Yes.
5.8, you don't worry about it. So it's about finding empirical and molecular formulas, and we're not going to get to it this year. Was it 105?
Yeah.
Okay, sorry. 105. 105, you're absolutely right. I don't know what's wrong with me. 105. Thank you, thank you. All right, so what we've got here is last time we talked about stock solutions. So you're going to measure out whatever volume you calculate. So this is the procedure you will do. You will calculate the volume of stock solution. And so you'll measure out whatever you've calculated. And you're probably going to measure out using so you're going to specify the size. If you need a 10 milliliter or a 20 milliliter or a 500 milliliter, whatever it is, that's how you would specify the size. If you needed 10 milliliters, you would use a 10 milliliter volumetric pipette. If you needed to measure out 500 milliliters, you would use a 500 milliliter graduated cylinder, because 500 milliliters is big and there ain't no pipettes that big. Have we used a pipette yet? No, we'll use one of those next week. Okay. So it depends how big the volume is, what piece of equipment you will use. So you might use a graduated cylinder, or you might use a volumetric pipette. If you have a larger volume, right, if you need 100 milliliters, say, you would probably use a graduated cylinder because they can contain more volume. If you wanted a smaller volume, particularly if you want 10 milliliters or 25 milliliters, and the reason I say those ones is because these are what we have at this school. Yeah? We have these two sizes. What is this kind of pipette called? It's the kind of pipette where you just have one marking on it. And that one marking is 25 milliliters. Just like in the volumetric flask, there was one marking for the 100 milliliters, right? This one, there is one marking, and it's either going to be for 25 milliliters, or in the case of a 10 milliliter one, it would be 10 milliliters. The reason we would like to use these ones is because they are super, super skinny. Okay? The narrower the piece of glassware is, the more precise you can get your volume. Does it make sense that like one tiny drop of liquid will make a bigger difference in height if the thing is very narrow, right? If you have a graduated cylinder, which is maybe this big around, as opposed to a pipette, which is like this big around, this one is going to be much more precise because whatever volume you add to it will make the height change a lot. Whereas you can add a fairly significant volume to the graduated cylinder and not see a great rise in height. Does that make sense? Okay. For any other volume, you can choose a graduated cylinder. In fact, should you ever want to, you can always choose a graduated cylinder. If the volume is less than 20 milliliters, and it's something weird like 17 milliliters or 7 milliliters, you can use a graduated pipette, which has all kinds of different volumes on it. So if you wanted 7 milliliters, you would start at the 3 milliliter mark and deliver it down to or actually you could start at the 0 and deliver it down to the 7, or you could start at the 3 and deliver it down to the tip. Don't worry about that too much. We don't use those. Not here. Okay? So we have taken our stock solution, we have put it into this pipette, and now we are going to transfer it into something. We are going to transfer the stock solution into, pick a size, 100 milliliter or 200 milliliter or 500 milliliter or whatever. Okay, whatever size you need. If you want to make 500 milliliter solution, choose 500 milliliters. If you want to make 1 liter of solution, choose a 1 liter vessel. Does that make sense? If you want to make 100 milliliters, choose a 100 milliliter vessel. And then you're going to pick your piece of equipment. You can use a volumetric flask or a graduated cylinder or a carboy. What the heck is a carboy? This is a carboy. Okay? It's basically a big vat. So if you've ever gone camping, you might have had something like this for your water, right? This one you wouldn't want to drink from because this has got, what is this in here? Hydrochloric acid. So don't drink from this one, okay? But it's got like a little tap on it. And this is really good for things like when we do, we have a titration lab that we're going to be doing in a little while, and we will use this stuff, okay? And because there are so many of you, and there's like many classes doing this, we need a huge volume to start with. And what you would all do is you would all come up here and, you know, get your little beaker with 50 milliliters in it or whatever. Yeah? But this is just a nice way of storing it. So maybe this would be a situation where I measure out 500 milliliters in a graduated cylinder, and then I pour it in there, and then I add water up until the 10 liter mark, and then I slosh it around. Yeah? Like it really is like very big and awkward and whatever, but that's what we do. But you guys will be working with smaller volumes because we cannot afford to waste that much chemicals and material and even water. It would be a big waste of water. Okay, most of your smaller volumes up to about 5 liters, you can use a volumetric flask. So I'm always going to give you a nice round volume. Okay, I'm going to give you a 50 milliliter or a 25 or a 250 or 100 or a 50 or a 1 to 5 liter kind of flask. Okay, those are your final volumes. If you have an irregular volume, I would suggest that you just make a regular volume and then not use all of it. However, should you want to make 37.5 milliliters, you could use a graduated cylinder and fill it up to 37.5 milliliters. It does seem a little bit silly though. Okay. And like I said, there is your carboy for large volumes. Okay, now there's a little note about acids here. If you have a concentrated acid and you add water to it, it produces a great amount of heat. It is very exothermic, which kind of means exit, thermic. And thermic has to do with thermal. What does thermal have to do with? Heat. So exit heat, exothermic, okay? And so this is a reaction, this mixing process causes a lot of heat to come out. And the problem is that if you have a very small volume, that heat doesn't have a lot of stuff, like a lot of liquid to get absorbed into, okay? If you have lots of water, it can absorb lots of heat without changing temperature. But if you have a small volume, it cannot absorb lots of heat. It will change temperature, and it might even boil. And what's going to happen if you now have boiling acid? Blah, blah. Okay, you don't want boiling acid. Boiling acid is a problem. Yes? Right? We do not want acid bubbling up all over the place. So there is a rule of thumb. So instead of doing that, we are going to make the volume bigger. so that there's more liquid, more water to absorb the heat. And we do that by, in our flask, instead of putting the acid in first, okay, so if we put the acid in first, you can see that would be just like a little tiny bit of volume. And then if we start throwing water into that, boil. Wah, 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 wah. Yes? So that's bad. But instead, what if we did this? What if we put water first? Yeah? And then we put in a little bit of the acid. Because we don't usually want that much acid. Usually it's like we're diluting something 1 in 10, so it would be like 10 milliliters in 100 total. Okay, so we put the acid in. Now, even though it's mixing, it's producing the same amount of heat, but there's a lot of water to absorb that heat, so the temperature doesn't rise as much. Okay, so we would put the water in first, then we would add the acid, and then we would swirl it, and then we would add more water up to the line. More H2O. Does that make sense? Okay. Now, in order to help you remember this, there is a little otter here to help you out. He's super cute. Look at him floating in the water. He has a little flask with some acid in it. Okay, and he's got safety goggles on. Yeah. And if you use a New York accent, oughta, which means ought to, as in you should, okay, ought to. Do as y'all oughta. Add acid to water. Yeah? Do as you oughta. Add acid to water. So don't put the acid first and then the water. Put the water first and then the acid. Anyway, hopefully the little otter will help you remember that. All right, we're going to go through this first exercise together. So this is on page 108. And the first thing we're going to do is we are going to add a decimal place so that we actually have some reasonable sig figs. Okay, so we're going to put a decimal place after that 100. Okay. We need, this is what we need. 100 milliliters of 0.4 molar potassium dihydrogen phosphate. What should we do with our 100 milliliters? How should we write that? We should change it to liters. What is that in liters? 0.100 liters. We have 0.40 molar. How should we rewrite that? Moles over liters. 0.040 moles per liter. Okay. And potassium dihydrogen phosphate. Potassium is K. Dihydrogen phosphate, you would have to look on your sheet. I can be your sheet for you today. It is H2PO4 minus. And so we have KH2PO4. And there we are. Okay. How much of a 0.5 molar stock solution would we need? When we say how much, what would we be measuring? Volume. So we're going to solve the problem using the following steps. Number one, we need to figure out how many moles of KH2PO4 we want in the final solution. So our final solution is this one. This is our final solution. Could we find the moles? Tell your partner how you would find the moles. Okay. Do you see how we've got liters and liters? Those can cancel out and we can be left with the moles. So what we're going to have is we're going to have 0.100 liters times 0.040 moles per liter. And that gives us 0.0040 moles. So that's how many we want in the final solution. Now, this question is actually a little bit silly. If we want 0.0040 moles, how much should we take from our stock solution? How many moles should we take? Don't think too hard. I'm going to rephrase the question for you. You want one donut. How many donuts should you take? One donut. Okay, so if we want 0.004 moles, how many moles should we take? 0.004 moles. That's how much we want in our stock solution. Okay, because the moles before dilution are the same as the moles after dilution. Yes? Sorry? 2 sig figs? Yeah, probably. There we go. Okay. So now we want the volume, which would be in, what's our unit there? Liters. Our stock solution, let's go back to the question. It says our stock solution is 0.50 molar. So we want, and we could rewrite that as 0.50 moles per liter. So I'm going to make that tidier. Okay, there we go. Could we take our moles per liter and our moles and figure out the volume? Tell your partner, how would you do that? How could you take the moles and the moles per liter and find the volume? What do we want on the bottom? Moles. What do we want on the top? Liters. So we're going to have, that pen did a weird thing. 0.50 moles per 1 liter. And we get 0.002? 008. Liters. Now, would it be reasonable, using the equipment that we have in our laboratory, to use the number 0.0080 liters. Is that like a nice number to work with? No. What could we do to make it a nice number? We can make it milliliters instead. Okay? So 2 ways to find milliliters. There's other ways as well. 0.0080 liters times, we want to cancel liters and find milliliters. There are 1,000 milliliters in 1 liter. So that is 8.0 milliliters. Or if you just want to move your decimal, you can just say 0.0, whoops, one more zero, 0.0080 liters, and you could move your decimal place. Now this time you're going to move your decimal place 1, 2, 3 to the right. If you cannot remember which way to move the decimal, just do this and it will make it easy, okay? Don't muck about with it unless you know what you're doing, okay? If you intuitively are okay, if you're like, milliliters are small, there should be more of them, then you're good to go. If that does not just pop into your brain as intuitive, maybe use the other method. Okay? So there we go. And that's it. So then what you would do is you would take that 8 milliliters, you would measure it out with a pipette, you would put it into your volumetric flask, and then you would fill it to the line with water, and then you would stopper it and invert to mix. Now, that being said, when you get to question 6, or no, actually, when you get to question 3, there's a part D that says, describe the procedure you will use to make the new solution. This will not be on the test. Okay? Because we have not done it yet, because it is Tuesday and your test is on Wednesday, because you already need to know one lab procedure.
Hold on a second. Wednesday?
What? Thursday. Your test is on Thursday. Did I say Wednesday? Oh my God. I'm so sorry. Your test is on Thursday. Thursday. You're like, tomorrow? What? No, it's not tomorrow.
No, yeah.
Next week we'll do the actual procedure itself, and I think that'll probably be more valuable than writing it on a test anyway. Okay? So, right now what you're going to do is you're going to work on pages 108 to 111 until you feel really good with this kind of calculation, at which point you can start reviewing overall. Okay? Use your book. If you need more, there is Hebden. Okay?
No. It's not worth that. Is that in the real sense? You want to go though? No. When you start without me, I have to go ask them. I swear.
Yeah.
Yeah.